Hi and welcome to Train Signal. This is the lesson where we're going to focus on customizing network load balancing. Another lesson covered the issue of setting up network load balancing. We're going to assume that you already know how to do that as you apply those skills to this section as we explore what we can do to be able to tweak NLB to meet our specific needs. The basic installation of NLB covers a wide variety of applications. It's a feature of the operating system targeted at web server farms and VPN server farms and things of that sort. We're going to explore a number of ways to be able to customize NLB for specific application needs in this section. So with that idea in mind, we're going to turn our attention to whether to target an application at a particular computer or at the whole collection of available hosts. In many cases, the latter option is the preferable one, but there are cases where a single host solution is good. We'll explore the idea of affinity. How do we know which computer of the collection of 2, 8, 2 dozen, whatever, computers we're going to send a particular request to? And the question of dealing with unneeded port ranges. What if there are ranges of ports that we might potentially get traffic on that our NLB cluster is just not intended to handle? Well, what happened by default, and how do we fix if we don't like that default behavior? So let me jump over to the server environment and let's start testing out what happens as we tweak some of these configuration settings. So here I am back on server 1. In an earlier lesson, you may recall that I set up an NLB cluster with 2 nodes, server 2 and server 3. The management software is on server 1, but that's not any problem with managing other servers out there in my environment. So server 2 and server 3 are accessible using a shared cluster IP address of 172.18.38.200. I've made that available via a DNS resolvable name NLB cluster 1, which resolves to that cluster IP address. We saw that I could target FTP requests at the cluster, and the cluster would determine which server would handle the request. Let's illustrate that over here. I'm going to jump over to PowerShell and FTP to NLB cluster 1. I'm going to use the -A command line switch to force an anonymous login. I've configured my FTP servers to allow anonymous. Doing FTP-A says do an anonymous login. It doesn't even bother to ask me for details about how to do that. It knows what to do. So I can see there that I was connected to server 2. I didn't say connect to server 2. I said connect to the cluster. And it figured out that server 2 was the right way to go. Now, why did it act that way? It's worth pointing out that if I quit out of FTP and connect in again, and quit out of FTP and connect in again, quit out of FTP and connect in again, each time it seems it's connecting me to server 2. Well, why is that? Well, that's default behavior in NLB. Let me show you exactly what I mean by that. I'm going to right-click the NLB cluster as a whole and pull up its cluster properties. Some of those properties are things that we've seen before. The cluster IP address, which is the overall IP address that describes the whole collection of computers. Cluster parameters include the name of the cluster, which type of cluster operation am I running. Am I using unicast operation where the cluster MAC address is applied to every cluster server? Am I using multicast where the original servers get to keep their IP addresses and MAC addresses, but they also inherit a multicast IP address with a multicast MAC address tied to it? Those are options that are configurable, and we address those in a different lesson. We're going to focus on this area here, port rules, because we haven't seen that in effect as of yet. It's here that we're able to describe to the cluster as a whole which kinds of traffic do we intend to handle. It's worth noting that an NLB cluster can handle multiple different kinds of incoming traffic and handle those kinds of traffic in different ways. The default behavior is that all traffic is handled, and it's all handled exactly the same way. And let's drill down into exactly how that looks. So you can see we're looking at a port rule here. This one is designed to take all incoming traffic on any incoming IP address. It's worth noting that an NLB cluster can potentially support multiple cluster IP addresses. We're only using one in this case. Down below, we're looking at the 65,536 possible ports that a request might be coming in upon. At the moment, we're tracking, again, all of them, listening for both TCP and UDP traffic. So the combination of those three things, an IP address, a protocol, a port number, together defines the idea of what's sometimes called a TCP socket. You can picture the 3 prongs in a US-style electric socket, positive, negative, and ground. Is that how that works? Positive, neutral, and ground. I'm nobody's idea of an electrician. Okay, so those three things are a socket. They're a description of the connection that we're going to make to an application on a server. So for all applications on this server, we're going to treat them the same way. And we're going to filter that traffic using one of three broad strategies. One of them might be to disable some range of ports. If I know that I'm not using anything above port number 1024, I might deliberately set aside ports 1025 through 65535 and disable that port range, saying, I'm not using that. It's worth noting that if I don't do something specific with every potentially incoming port, the default behavior is that one particular host in the cluster is going to get slammed with all of that traffic, whether it likes it or not. Hardly seems fair, but them's the rules. If I don't deliberately disable unwanted incoming traffic, it is going to get handled by the cluster somehow, regardless of whether there's software waiting on those servers to handle that or not. So one good strategy is to disable any ports you know you're definitely not planning on routing traffic for. That way those hosts will simply drop that traffic and say, yep, I'm not responsible for handling that, and let it go. But let me deal with the other end of the scheme here. We've got, in this particular case, we're talking about FTP servers. Well, FTP servers use port 20 for control traffic and 21 for a flow of data. I want to make sure that we handle that traffic wisely. I don't want to disable that port range. I could choose single host based configuration, in which case all FTP traffic goes to some particular server. Which one? Well, that depends on that priority number that you might have seen configured in a different lesson. We'll focus on it again here in a moment as well. The third option is multiple host configuration. Multiple host configuration is going to give us a couple of different options to be able to describe how to distribute this incoming traffic across what might be 2 or 3 or 4 or as many as a dozen or a couple of dozen servers. The three main types of affinity at our disposal include no affinity, single affinity, and class C affinity. Single again is the default. Single affinity says that when a request comes in from a particular IP address, the cluster is going to pick some particular node to handle that request, and from that point on, that same node is going to handle all the traffic from that same client machine. Unless, of course, the system reconverges around a different strategy because we've added more nodes and it decides to reconfigure its configuration. But in general, requests from the same client hit the same server, and in general that works just fine. If I've got a large number of clients, they each get their own personal server, if you want to think of it that way, and that server will take care of all of that client's requests. That's single affinity. None affinity is one that says there's not even a specific need for a repeat request from the same client to go back to the same clustered server. I can send that request to any server. It doesn't matter. Frontier web applications may well use that one, saying, yeah, it doesn't matter. Whichever one makes sense, let it reply. Because the only thing happening at that server is serving up maybe static HTML pages. We're not storing any state. There's no information about that session being stored to that computer that we need to recall at a later point. With that idea in mind, why bother? A third option is Class C affinity. And the idea of Class C affinity is that we want to be able to ensure that computers that share a Class C subnet all get connected to the same server. So if I've got requests from multiple subnets, each subnet stakes out a favorite server, and traffic goes there from that subnet. There are situations where an application connects in through a series of proxy devices of some sort, and those proxy devices, although representing the same individual person, are coming in by way of multiple proxied devices in my network, and as such, because they all share the same Class C IP address range, they should all be handled together by the same clustered node. That one's not commonly configured, but there are circumstances where it makes sense. It's good to know that it's there. So by way of demonstration, let's change the behavior of my FTP traffic from single affinity to none, just to see what happens. Let me OK that change. We've now got two port rules. This used to be the default port rule until I modified it into a block everything above the well-known ports area. and I've got a let's handle FTP rule here. That change has converged. Let's take a look at what happens on the client. I'm going to go back to my PowerShell window. I'm going to quit out of my existing session talking to server 2 and fire up another FTP targeted at the NLB cluster. Okay, we hit server 2. Let me quit. Hey, that time server 3 took up my request. Let me quit again. Let me connect in again. Server 3. Again. Server 3. Again. Server 2. So we're not exactly alternating, but we are distributing. The servers are agreed amongst one another about which requests are going to be handled by which one of them and why. And instantaneously, as requests come in, all the servers in my cluster hear that request simultaneously, but only one of them elects to respond to it. The others know instinctively that that message is not meant for them, and they drop those corresponding packets. So how good of a balance do we have between server 2 and server 3 here? Are we fairly distributing our load is an interesting question. One way to do that would be to do a long series of these. And rather than type a series of commands to open and close and open and close, I'm going to write a short snippet of PowerShell code to do that work for me. So I'm going to quit out of FTP. I'm going to use the FTP-A command, NLB cluster. But I'm also going to use another interesting command line switch for FTP called /s. The /s switch, it lets you identify a command, more specifically a file that contains a list of FTP commands that you would like to issue at the time that you get connected. And the one that I'm going to use is the quit command. So actually I put the word quit inside of that file. If you're curious, that's what's in there. So it logs me in and logs me out. If I recall that command, logs me in and logs me out. Now, one interesting question is which server number are we getting each time? What I'm going to do is I'm going to issue this command a bunch of times. And through the magic of PowerShell, I'm going to say count from 1 to 20 PowerShell and take that set of numbers, and for each one of those numbers in that list, I want to perform this task we've just been describing. So 20 times I want to connect and quit, and connect and quit, connect and quit, and connect and quit. Okay, that seems to be working pretty well. What I'd like to do is be able to capture somehow the information that tells me which of these numbers we've got. So what I'm going to do is I'm going to take all of the output coming from this command, and I'm going to group it into logical collections. Certainly there's a lot of repetitive text here. I'm going to take all that output and group it logically with a command called group-object. (20 logins), and we can see that we got 11 requests that were handled by New York City server 3, and we got 9 that were picked up by server 2. So 11 to 9, that's pretty even. Let me go one step further with my querying and filter the output in that grouping area just for those things where the object in question has a name property that is shaped like some string of characters and the word welcome and some other string of characters. And I missed an important character there. All right, 9 to 11, 11 to 9, 11 to 9, 14 to 6. Okay, it was a little overbalanced in favor of server 3 that time around. Server 3 wins 13 to 7. Server 3 wins 12 to 8. Server 2 wins 15 to 5. So it's never necessarily exactly perfect for any given string of requests, but in general it's going to average out. These computers are by default distributing more or less equally these incoming pieces of traffic. and that's actually a configuration inside of the NLB client itself. For the sake of argument, let's try fixing that. Let's tweak that a little bit. Maybe we know that server 2 is twice as capable as server 3. It's a very powerful computer. By default, server 2 and server 3 are sharing this traffic equally. But I might deliberately go configure the properties of this particular network load balancing host to configure its port rules, and just by way of flying through host parameters, there's the dedicated IP address for server 2. It will start in a stopped state if I don't tell it otherwise. Cluster IP address that we're using. Cluster parameters it's inheriting again from the cluster. Port rules, including a rule that says ports 2021 are handled equally. And here we see a bit of interface that we did not see in the parent dialog box in the properties of the cluster as a whole. I can see that this server wants to handle traffic equally. Let me turn that off. We can see that this server uses a load weight of 50. That is an abstract number. There's no special meaning to that. That's not a certain number of requests. It's not a certain amount of megabits of bandwidth. It's just a scalar number meant to abstractly represent how much stress of the overall total coming in this server wants to eat. And at the moment, this one's got a load weight of 50. What I'd like to do is I'd like this one to take on twice the amount of work as server 3. Well, server 3 is also configured at 50, so I could take this load weight up to 100. That would work. Or alternatively, I could leave this at 50, and I can go over to server 3 instead, and configure that same port rule for server 3 to dial its load weight down to 25. The numbers, again, don't really matter critically. I could equally well have set server 2 to 2 and server 3 to 1. I could have set server 2 to 38 and server 3 to 19. What's important here is the 2 to 1 ratio. So let's see if we can put that into effect. I'm going to OK these changes. So we wait a moment, we'll see the cluster converge. There we go, and I'll do an F5 refresh to confirm that everything looks kosher, and it does. We have a converged status on both hosts. Let me do another string of 20 FTP logins. 14 to 6 in favor of server 2. 11 to 9 in favor of server 2. Server 2 wins again, 13 to 7. 11 to 9, server 3 won that time. Server 2 ahead, 12 to 8. Server 2, 15 to 5. Server 2, 16 to 4. Server 2, 14 to 6. You're seeing server 2 winning the race nearly all the time here in the amount of requests that were handled by it. That is not a mistake. That is a direct consequence of our calibrating the port rule to deliberately throw a certain amount of traffic at server 2 instead of server 3. Now I can do that for individual applications by identifying what port number is applied to each. I can target those things at different cluster IP addresses. I can have the same cluster with more than one cluster IP. This is a technique sometimes referred to as virtual clusters. From the outside world, more than one NLB cluster, all being implemented on the same physical set of servers, cooperating together using different combinations of port rules, each of which listening on a particular cluster IP address. Let me show you a couple of other important things that you can do with the NLB Manager before we bring this lesson to a close. What happens if I know that a particular NLB server needs some maintenance? I want to take it offline, I want to be able to replace a hard drive, I want to be able to change out some hardware, I want to vacuum out the dust bunnies. Server 3 perhaps is due for some maintenance. It's starting to act a little funny. So what am I going to do? Well, what I want to do is I want to be able to take it out of the cluster. But what if it's currently handling requests? What if there are people currently connected in doing some work with that computer? Well, what I can do is I can right-click that server and configure its host behavior to suspend. That's a pause. I have a corresponding resume. I could just stop it, but of course that would just kill it right where it is, and any requests that are not yet finished would be terminated. That's going to make clients unhappy. We don't want to do that. A better option in lots of cases is drain stop. The term drain is a way of saying I want to let this computer continue doing its work, not accepting any new requests. No new requests will be targeted at this host. But anything that's currently being worked on can go ahead and finish. And once it's done draining, once we've run out of additional things for this computer to do, once it's finished all of its currently allocated work, knowing that it's not taking on any more, it will in fact stop. Once it's stopped, we can take that server offline, we can vacuum out the dust bunnies, we can install the new solid-state drive in it and power back up. Once it's up, we can re-include it in the cluster, start it up using this part of my console, and we're back in business. So network load balancing provides some really rather substantial benefits, and being able to calibrate the detailed settings of which we've seen here will give you the ability to create a range of application support scenarios on your NLB cluster to handle a variety of different applications with different kinds of needs. I hope that's helpful to you in your organization and look forward to sharing more with you in the next lesson.